Your brain can't process the most horrifying distances in space. You probably think you understand how big the universe is, then you discover that light, the fastest thing in existence, can spend millions of years crossing a single region of space. The human brain evolved to understand miles, cities, and continents. Space operates on a completely different scale. Distances between stars, galaxies, and cosmic structures are so vast that even the numbers themselves begin to lose meaning. The limit of human perception. Space does something strange to your mind the moment you try to understand it properly. Not emotionally, not philosophically, but in a direct physical sense where your brain simply stops being able to hold the full picture. It does not matter how smart someone is or how many numbers they know. There is a hard limit in human perception where distance stops feeling real and starts becoming something your brain compresses into symbols that no longer match reality. Start with something simple and familiar: the Earth and the Moon. The distance between them is about 384,400 kilometers. That number sounds large, but your mind still tries to reduce it into something understandable, like a long road trip or a stretched flight path. Now slow that down and look at the time it takes for light to travel that distance, about 1.3 seconds. That means every time you look at the Moon, you are not seeing it as it is right now, but as it was more than a second ago. Already, the brain starts to lose grip because nothing in daily life works like that. Now move further. The Sun is not just far away. It is about 149.6 million kilometers from Earth. That distance is so large that if you tried to imagine it as a straight line, it stops behaving like a normal distance and starts acting like an abstract idea. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. That means when you look at the Sun, you are seeing it as it was more than 8 minutes ago, not in real time. Even this already breaks normal thinking because your brain is used to everything it sees being immediate and local. But this is still the comfortable zone. This is still inside what humans can loosely imagine because it involves familiar objects like a star and a planet. The real breakdown begins when you step outside the Sun's influence and look at the rest of the solar system as actual space instead of a diagram. Between planets, the distances are not just bigger, they are mostly empty in a way that removes any sense of structure. If Earth were a small marble and the Sun were placed in a city centre, the next nearest planets would not sit close by. They would be spread far across empty regions with nothing in between except vacuum. When you move toward Jupiter, Saturn, Uranus and Neptune, the distances between them stop behaving like steps and start behaving like separate, isolated zones. Light from the Sun takes about 43 minutes to reach Saturn and nearly 4 hours to reach Neptune. That means even inside our own solar system, signals are delayed by hours depending on where you are. Your brain does not naturally model anything like this because on Earth, distances are so small that light delay is basically zero for human experience. Now expand further and something more extreme appears. The solar system is not a tight cluster. It is a widespread region of scattered bodies surrounded by almost total emptiness. Beyond Neptune lies the Kuiper Belt, a region filled with icy objects that are still part of the Sun's gravitational system. But even here, the distances are not like regions in a normal sense. They are gaps so large that even spacecraft moving for years barely make progress through them. Voyager 1, one of the farthest human-made objects, took decades just to reach the edge of the solar system. Even now, after more than 40 years of travel, it is still within a fraction of interstellar space. This is where the first serious breakdown begins, because human intuition assumes that travel is a matter of time and effort. But at this scale, even constant motion barely changes position in any meaningful way. Now step past the solar system completely. This is where distance stops being something your brain can convert into everyday meaning. The nearest star outside the Sun's system is Proxima Centauri, and it sits at about 4.24 light-years away. A light-year is not a measure of time, but a measure of distance, defined by how far light travels in 1 year. That already removes the brain's normal reference system because no object in daily life is measured in anything close to that scale. If you try to convert it into kilometres, the number becomes so large it stops feeling like a measurement. It becomes a wall of digits that no longer represents space in your mind. Even if you ignore the numbers and try to picture it as travel, it fails again. The fastest spacecraft ever built would take tens of thousands of years to reach that star. Not centuries, not a few generations, but time spans longer than recorded human civilization. At this point, the brain tries to compress the information. It stops seeing distance as space and starts treating it as labels. Nearby star, far star, edge of system. But none of these labels reflect actual physical spacing. Between stars, there is not a crowded field. There is mostly empty space with rare points of matter separated by distances so large that even light needs years to cross them. Now, step further into the Milky Way. This is where human perception stops having any usable reference. The Milky Way is about 100,000 to 200,000 light-years wide. Inside it are hundreds of billions of stars. But the key point is not the number of stars, it is the spacing between them. Even in a galaxy filled with stars, the average distance between one star and the next is still measured in light-years. This means that even inside a structure that looks dense in images, most of it is still empty space. If you place the Sun anywhere else in the galaxy, the night sky would not suddenly become crowded with nearby suns. Most directions would still be dark, because the distances are too large for stars to fill the sky in a continuous way. The brain struggles here because it expects density to behave like crowds or clusters. But space does not follow that rule. Now consider motion inside this system. The Sun is not stationary. It moves around the center of the galaxy at about 828,000 kilometers per hour. Even at that speed, it takes roughly 225 million years to complete one orbit. That means entire geological eras on Earth pass before a single galactic orbit completes. The brain cannot hold this scale because it has no internal mechanism for tracking events across millions of years, while also tracking physical distance at the same time. At this level, distance is no longer just space. It becomes tied to time in a way that removes everyday meaning. Light from different parts of the galaxy can take thousands or even tens of thousands of years to reach Earth. What you see in the night sky is not a current snapshot of the galaxy, but a mix of different times spread across a vast range of history. Now expand again. Beyond the Milky Way are other galaxies, and between galaxies the distances increase again by orders of magnitude. The Andromeda Galaxy, the closest large galaxy to ours, is about 2.5 million light-years away. That number is already beyond intuitive reach. If you try to imagine traveling that distance, even at the speed of light, it takes millions of years, and light is the fastest thing in the universe. At this scale, even the idea of nearby breaks. Two galaxies that are called neighbors are still separated by distances so large that any normal comparison fails. If the solar system is already mostly empty space, then intergalactic space is emptiness multiplied again, with only rare structures scattered across vast gaps. Now consider the observable universe, the part of space that we can see, because light has had time to reach us. Its diameter is about 93 billion light-years. This is not the size of everything that exists, but only the part we can detect. That alone is already beyond anything the brain can map. The idea that a signal starting at one end of this region takes tens of billions of years to reach the other end removes all familiar structure from the concept of distance. At this scale, even basic comparison fails. There is no object in daily life, no natural reference, no human experience that can anchor these numbers. The brain attempts to compress it by ignoring detail and replacing it with simple categories like very far or extreme distance. But these categories carry no real physical meaning anymore. What makes this even more difficult is not just the size, but the way light itself behaves across these distances. Every object you see in space is seen in the past. Some objects are seen as they were seconds ago, others minutes, hours, years, or millions of years ago. The deeper you look into space, the further back in time you are also looking. This means distance is not just spatial separation, but also a delay in information that increases with scale. At the same time, the brain continues trying to simplify everything into local experience. It treats space like something that can be walked through or driven across, even when the actual distances make that impossible on any meaningful timescale. This mismatch between physical reality and mental modelling is where perception starts to fail completely. Even the idea of empty space is misunderstood by intuition. On Earth, empty space means a room or a gap between objects. In space, empty means something entirely different. It means regions so large that if all matter in the solar system were removed, the remaining volume would still be almost entirely empty. And even within galaxies, most of the volume is still empty space, with matter occupying only tiny fractions of the total region. As the scale increases, the brain keeps applying the same internal rules it uses for Earth-scale thinking, but those rules stop matching reality. Distance stops being a number you can feel and becomes something the mind has to store without truly visualizing. The further you go outward, the more the brain relies on compression, turning real physical structure into simplified mental placeholders that no longer reflect the actual structure of the universe. How humans actually perceive distance. The human brain does not measure distance in a clean or direct way. It builds a rough model based on signals that come from the eyes, the body, and memory working together at the same time. What you see as distance is not actually distance itself, but a mix of light patterns, focus changes in the eyes, motion cues, and past experience stored in the brain. This system works extremely well on Earth, where most distances are small, predictable, and filled with reference points like buildings, trees, roads, and people. But the moment you move beyond that scale, the system starts to fail in quiet but important ways that you do not notice at first. The eyes are the first limit. Each eye captures light through the retina, which is a thin layer of cells that converts light into electrical signals. But the retina is not infinitely detailed. It has a highest possible resolution, and beyond that, extra detail simply does not exist in what you see. This means that faraway objects are not only smaller in your view, they also lose detail in a way that cannot be recovered, no matter how hard you focus. When something moves farther away, it does not just shrink, it becomes less defined until it eventually turns into a shape that the brain fills in rather than directly sees. At normal Earth distances, this does not matter much because your brain can still use context to understand what something is. A car in the distance is still a car because you have seen enough cars in your life to recognize the pattern even when detail is missing. But the key point is that recognition replaces actual visual information. The brain is not seeing the full object, it is guessing based on partial data. This is already the first step where perception becomes less about reality and more about interpretation. Depth perception adds another layer, but it also has strict limits. The brain uses two eyes to compare slightly different images, and from that difference it estimates how far away something is. This works well for short and medium distances, especially within rooms or open spaces where objects are relatively close. But as distance increases, the difference between what each eye sees becomes smaller and smaller until it is almost nothing. At that point, the brain can no longer rely on stereo vision, and it switches to secondary cues like size, overlap, and motion. These secondary cues are not precise. They are learned patterns based on everyday experience. For example, if something appears smaller, the brain assumes it is farther away. If something moves slowly across your field of view, it is assumed to be far. If something blocks another object, it is assumed to be closer. These rules work in normal environments, but they are not measurements of real distance. They are shortcuts that usually produce a correct guess. The problem is that space does not follow these everyday rules. In space, size is not always connected to distance in a way your brain expects. A small object might be extremely large but far away, or a bright object might appear small simply because it is emitting light from a great distance. Without familiar reference points, the brain loses its ability to apply its normal shortcuts, and depth perception becomes unreliable almost immediately. At that point, another system takes over, the brain's internal mapping system. Deep inside the brain is a region called the hippocampus, which is responsible for building mental maps of the environment. This system is constantly active, even when you are not thinking about it. It stores information about locations, paths, directions, and spatial relationships between objects. It is the reason you can walk through your neighborhood without thinking, or remember the layout of a familiar room without needing to look around. The hippocampus builds maps based on experience, not raw measurement. It learns patterns, like how long it takes to walk somewhere, what direction a place is relative to another, and what sequence of turns leads from one point to another. These maps are flexible but limited. They are designed for environments where movement happens at human speed, and distances are measured in meters, not millions of kilometers. Because of this design, the brain struggles when distances stop having physical reference points. It cannot build a reliable map when there is no movement experience attached to it. You can understand that the moon is far away, but your brain cannot store that distance in the same way it stores walking from one room to another. The information exists, but it is not integrated into a usable mental model. It becomes abstract data instead of lived spatial understanding. This is where a deeper limitation appears, not in the eyes or memory alone, but in how the brain compresses information. The brain does not store every detail of reality. It simplifies constantly. It takes large amounts of information and reduces them into patterns that are easier to store and recall. This process is essential for survival, because without it, the brain would be overloaded with data from every direction. When it comes to distance, this compression becomes extreme. Everything beyond a certain range stops being stored as a precise spatial value and instead becomes a symbolic label. The moon is not stored as 384,400 kilometers away in any active sense during normal thought. Instead, it is stored as far but reachable. The sun becomes very far and very large. Stars become extremely far points of light. These labels are useful for quick thinking, but they remove actual scale from perception. This is why two distances that are vastly different in reality can feel almost the same in the mind. The distance to the moon and the distance to the sun are both far in everyday thinking, even though one is thousands of times greater than the other. The brain does not maintain proportional scaling at large distances because it stops updating its internal model with precise measurement once the scale exceeds daily use. The compression problem becomes more visible when you look at how humans imagine space visually. Most people picture space as a kind of map where objects float in clear positions with visible spacing between them. But this is not how perception actually works. The brain does not maintain a full spatial model of the solar system or galaxy in real time. Instead, it stores fragments that are assembled only when needed, and even then, the assembly is incomplete and simplified. For example, when you think of planets in the solar system, you might imagine them lined up or spaced evenly in a neat arrangement. In reality, the spacing is irregular, and the distances are so large that if the planets were drawn to scale with correct spacing, most diagrams would be almost completely empty. The brain avoids this level of emptiness because it cannot easily process large areas of nothing. So it compresses space into something more visually manageable, even if it is inaccurate. Another important limit is how motion affects distance perception. On Earth, movement helps confirm distance. If you walk toward an object, it grows larger at a predictable rate. If you move sideways, objects shift in perspective. These changes allow the brain to calculate distance indirectly through motion. But this only works when movement produces visible change within a short time. In space, motion changes are often too slow to detect. A spacecraft travelling at high speed still appears almost stationary when compared to cosmic distances. Even planets moving around the Sun do so over long time periods that are not visible in real time. Because of this, the brain cannot use motion as a reliable feedback system beyond Earth-like scales. Time delay in light adds another hidden layer to this problem. Everything you see in space is delayed information. The Moon is a second-old image. The Sun is an 8-minute-old image. Stars are years or thousands of years old images. Galaxies are millions of years old images. This means that distance is directly tied to time, but the brain does not naturally combine these two concepts when forming visual understanding. Instead, the brain treats visual input as immediate unless it is told otherwise. This creates a silent mismatch between what is seen and what is physically true. The further away something is, the more outdated the information becomes, but the brain still processes it as if it is current. This delay is not noticeable in daily life, so it is not part of natural perception. Evolution plays a major role in why all of this exists. Human perception evolved in environments where survival depended on short-range accuracy. Finding food, avoiding danger, navigating terrain, and recognizing other humans all happen within a relatively small spatial range. There was no evolutionary pressure to develop a system that understands distances across planets or stars, because such scales never affected survival directly. Because of this, the brain optimized for efficiency, not accuracy at extreme scales. It built systems that are fast, good enough, and low energy. This is why shortcuts like size comparison, motion tracking, and pattern recognition exist. They reduce the need for exact calculation. But these shortcuts only remain valid within a narrow range of real-world conditions. Once you move outside that range, the same shortcuts start producing misleading results. A star that looks small is not small, it is simply far away. A bright object is not necessarily close, it may just be extremely luminous. A dark gap in space is not empty in a simple sense. It may span distances so large that normal intuition cannot detect structure inside it. The brain's final major limitation in distance perception is that it cannot naturally hold exponential scale. Human intuition is built for linear change, where doubling something feels like a clear step up. But space operates on scales where each step increases by factors that are not linear, but exponential. A jump from Earth to the Moon is large, but a jump from Earth to the Sun is already hundreds of times larger. From the Sun to the nearest star is tens of thousands of times larger again. From stars to galaxies increases again by millions of times. At each stage, the brain resets its sense of far because it has no stable internal unit for comparison. What was once extreme distance becomes near in cosmic terms, not because it is actually close, but because everything else is so much larger that the previous reference loses meaning. This constant resetting is where perception fully breaks down. The brain continues to function, continues to process images and numbers, but it no longer maintains a consistent sense of scale. Instead, it switches between local understanding and abstract labeling, depending on context. What remains is not a true spatial model of the universe, but a layered system of approximations that work only in specific ranges and fail when stretched too far beyond Earth-based experience. The first breakpoint, the Moon. The first time human perception truly starts to crack is not at the edge of the solar system or in deep space, but right at the Moon, the closest natural object to Earth. It looks simple in the sky, steady and familiar, something you can point at easily and feel like you understand. But the moment you start breaking down what that distance really means in physical terms, the brain begins to lose its grip on scale in a way that is subtle at first, but becomes harder to ignore the more you look into it. The Moon sits at an average distance of about 384,400 kilometers from Earth, a number that already pushes beyond normal human experience because there is nothing in daily life that comes close to that kind of separation in a single stretch. To understand what this distance actually means, it helps to remove all familiar references and just look at motion itself. If you were to travel to the moon in a passenger jet flying at around 900 kilometers per hour, with no stops and perfect conditions, the journey would take roughly 17 days. That already removes the idea that the moon is near in any practical sense, because no human trip on Earth is designed to last that long without interruption. Even spacecraft, which move far faster than planes, still take around 3 days to reach it. That delay alone shows that the moon is not a nearby object in the way the brain first assumes when it looks up at the sky. The strange part is that none of this matches what the eye sees. The moon appears small, bright and fixed in a way that suggests closeness. It sits in the sky like an object that could be reached if only you had enough height or time. And this visual impression is the first major trap the brain falls into. Human vision is not designed to measure absolute distance in open space. It is designed to recognize objects on Earth where size, texture, and context are usually give enough clues to estimate how far something is. The moon removes all of those cues at once, leaving only brightness and shape, which are not reliable indicators of distance at all. This is where the first real illusion begins. The brain uses brightness and apparent size as shortcuts. The moon looks large enough to be significant, but small enough to feel approachable, and that combination creates a false sense of proximity. There is nothing in the sky next to it to compare it against in a meaningful way. So the brain fills in the gap with assumptions based on Earth-level experience. On Earth, objects that look similar in size are often within reachable distance, so the brain applies the same logic upward into space, even though the conditions are completely different. The reality of the moon's size makes this even more confusing. The moon has a diameter of about 3,474 kilometers, which is roughly a quarter of Earth's size. That means it is not a small object floating nearby, but a large planetary body in its own right. If the moon were placed on Earth's surface, it would span entire continents. Yet from Earth, it looks like a small circle in the sky, because distance compresses its appearance so heavily that the brain strips away its true scale. This compression is automatic and happens before conscious thought can correct it. The distance between Earth and the moon also introduces a delay in light that is small but important. Light takes about 1.3 seconds to travel from the moon to Earth. That means every image of the moon you see is slightly delayed, not by minutes or hours, but still delayed enough to show that even the closest celestial object is not experienced in real time. This delay is so small that it does not affect daily perception, but it is the first clear sign that what you are seeing is not immediate reality, but a slightly older version of it. When Apollo missions traveled to the moon, they provided a physical reference that made this distance real in a way that no visual observation alone could achieve. The Apollo spacecraft took about 3 days to reach lunar orbit, traveling through a region of space that is completely empty compared to Earth standards. During this journey, astronauts experienced a gradual fading of Earth's presence. The planet slowly shrank in their view, not disappearing suddenly, but becoming a smaller and more isolated object with every hour of travel. This shrinking effect is important because it shows how distance in space is not perceived as a jump, but as a continuous reduction in size and brightness over time. From Earth, the Moon and Sun appear similar in size in the sky, which creates another layer of confusion. The Sun is about 400 times larger than the Moon, but also about 400 times farther away, which makes both appear nearly identical in angular size when viewed from Earth. This is not a coincidence. It is a rare geometric alignment that creates one of the strongest visual illusions in human perception. The brain does not calculate actual size or distance directly. It relies on angular size, which is how large something appears in your field of view. When two completely different objects produce similar angular sizes, the brain treats them as comparable in scale, even though their actual physical sizes are vastly different. This is where scale distortion begins to take root. The Moon becomes a reference point for distance, even though it is not actually a good reference. People often use it as a mental benchmark for space nearby, but this benchmark is already misleading because it represents a scale that is far beyond anything experienced on Earth. Once the brain accepts the Moon as near, everything beyond it becomes harder to scale correctly because there is no intermediate step between Earth-level distances and lunar distance that feels natural. If you try to imagine the Moon's distance using everyday movement, the problem becomes even clearer. Walking to the Moon is impossible within any human timescale. Driving to the Moon is equally meaningless. Even continuous motion at extreme speeds does not make the distance feel smaller in a way that the brain can fully process. This is because the brain is not built to handle uninterrupted long-distance scaling without landmarks. On Earth, distance is always broken by objects, terrain changes, and visual markers. In space, there are none of these markers between Earth and the Moon, so the brain loses its ability to divide the distance into manageable parts. This lack of reference points creates a silent failure in perception. The Moon is seen as a single object in a single location, not as a point in a vast empty region that stretches almost 400,000 kilometres. The emptiness between Earth and the Moon is not visually represented in the mind because emptiness itself does not produce sensory input. The brain fills this gap by ignoring it, compressing the entire space into a simple mental label of sky above Earth. Even when you know the actual distance intellectually, the brain still does not translate that knowledge into visual understanding. You can repeat the number 384,400 kilometres, but it does not automatically convert into a mental image that matches reality. Instead, it stays as a number disconnected from physical feeling. This separation between knowledge and perception is one of the key reasons why space distances feel unreal, even when they are fully understood in theory. As spacecraft travel to the Moon, another layer of scale distortion becomes visible. During launch, the spacecraft rapidly leaves Earth's surface, and within minutes it is already above the atmosphere. At this stage, the Earth still looks large and dominant, but as the spacecraft continues outward, Earth begins to shrink at a noticeable rate. This shrinking is not linear in perception. At first, the change feels slow, then it becomes more noticeable, and then it suddenly feels like Earth is becoming distant very quickly, even though the spacecraft is moving at a constant speed. This shift in perception happens because the brain does not measure distance directly. It measures change in visual size over time. When that change crosses a certain threshold, the sense of distance becomes unstable. The Earth goes from being a dominant presence in the sky to a small blue sphere within a few days of travel. And this transformation is one of the first real experiences where human perception of scale is directly challenged by physical movement. Another important detail is how silence and emptiness affect the perception of distance. Between Earth and the Moon, there is no air, no sound, and no medium that can carry familiar sensory cues. On Earth, distance is often linked to sound delay, wind, or environmental changes that give indirect clues about space. In the vacuum of space, none of these cues exist. This removes another layer of perception that the brain normally depends on, making distance feel even less grounded in physical reality. Even radio communication between Earth and the Moon is delayed, reinforcing the idea that information itself has to travel across space. That delay is small, but it is enough to show that even communication is not instantaneous beyond Earth. This creates a situation where every interaction between Earth and lunar missions is slightly offset in time, and this offset becomes part of the structure of how distance is experienced. At this stage, the Moon is no longer just a bright object in the sky. It becomes the first point where human perception begins to separate visual appearance from physical reality. The brain continues to treat it as familiar and close, but the underlying measurements show that it is already far beyond anything that can be compared to Earth-based distance. This is the first clear point where scale distortion becomes unavoidable, because the simplest celestial object reveals that human perception is not built to handle space, even at its closest range. The Sun, where intuition fails first. The moment the mind tries to properly understand the Sun as a physical object in space, rather than just a bright circle in the sky, something important starts to break in how distance is processed. Because the Sun sits at a scale where Earth-based intuition stops giving reliable answers while still pretending it does. And this creates a silent mismatch between what the brain assumes and what physics actually describes. The distance from Earth to the Sun is about 149.6 million kilometers, a number that already removes it from anything humans can experience directly, yet the brain still tries to force it into familiar categories like far or very far, even though those words no longer carry real meaning at this scale. If you try to imagine this distance using movement, the failure becomes obvious very quickly, because even the fastest aircraft on Earth would take many years of non-stop travel to reach the Sun. And even spacecraft designed for deep space missions still require months just to reach a fraction of that distance. There is no physical journey in human life that can be used as a reference point, so the brain loses its usual way of anchoring distance through experience. Instead, it falls back on abstract numbers that do not connect to any lived feeling, which is where perception begins to disconnect from reality in a more serious way. The Sun itself looks simple from Earth, a stable glowing disk in the sky that rises and sets in a predictable pattern. But this visual simplicity hides the fact that what you are seeing is not the Sun as it exists at that exact moment, but the Sun as it was 8 minutes and 20 seconds ago. Light takes time to travel across space, and at this distance, that delay becomes noticeable in a physical sense, even if it is not noticeable in daily life. Every photon entering your eyes has been traveling through space for over 8 minutes before it reaches you, which means your view of the Sun is always slightly behind reality. This delay is the first major point where the brain starts to fail in connecting distance with time in a natural way. Because on Earth, light travel time is so fast that it can be ignored. But in space, it becomes a real factor that shapes what you are actually seeing. The Sun you observe is effectively a memory of the Sun, not a live image, and this idea becomes more important as distance increases further into space. The brain does not naturally account for this delay when forming visual impressions, so it continues to treat the Sun as an immediate object, even though it is physically separated from you by both distance and time. To understand the scale more clearly, it helps to compare the Sun's distance with the size of Earth itself, because Earth has a diameter of about 12,742 kilometers, while the distance from Earth to the Sun is about 149.6 million kilometers. This means that if you were to line up Earths end-to-end along the path to the Sun, you would need more than 11,000 Earths just to fill the gap. This comparison shows that the space between Earth and the Sun is not just empty space, but a vast gap that completely removes any sense of closeness that the brain tries to assign to it when looking at the sky. Even this comparison does not fully capture how the brain misreads the situation, because when you look at the Sun, it does not appear 149.6 million kilometers away. It appears as a small but intense object in the sky, and this appearance tricks the brain into compressing its distance into something far smaller than it actually is. The brain uses angular size, which is how large an object appears in your field of view. And since the Sun and Moon appear almost identical in size from Earth, the brain tends to place them into similar mental categories, even though their actual physical scales are completely different. The reason the Sun and Moon appear the same size in the sky is not because they are similar in size, but because of a rare alignment where the Sun is about 400 times larger than the Moon, but also about 400 times farther away. This coincidence creates a visual overlap that removes scale differences from direct perception. The brain sees two similar circles and assumes a relationship that does not exist in physical reality, which leads to one of the earliest distortions in human understanding of cosmic distance. Once this distortion is accepted without correction, everything built on top of it becomes harder to scale correctly. The Sun becomes a reference point for near space, even though it is already deep into space in physical terms. This is where intuition begins to fail in a structured way, because the brain is trying to use Earth-based rules to interpret a situation that does not follow Earth-based conditions. Another key failure appears when you consider how light intensity works at this distance. The Sun delivers enough energy to Earth to support all weather, oceans, and life, yet it is still 149.6 million kilometers away. The brain tends to associate intensity with closeness, so something that feels warm or bright is often assumed to be near. But in this case, the Sun breaks that rule completely, because its energy output is so large that it remains extremely powerful even after travelling across a vast empty space. This creates another layer of misunderstanding, where the brain tries to link brightness with distance, but fails because the Sun is both extremely bright and extremely far at the same time. The result is a mismatch between sensory input and physical cause, which the brain resolves by simplifying the Sun into a single fixed idea instead of a dynamic physical object located at a specific scale. When spacecraft are used to measure or approach the Sun's environment, the scale becomes even more apparent. Missions like solar probes travel directly into regions of extreme heat and radiation. But even these journeys take time that feels slow compared to the scale involved. The spacecraft gradually moves away from Earth, and over days and weeks, Earth becomes smaller in the background while the Sun remains dominant in the forward direction. This gradual shift reinforces the idea that distance in space is not a sudden change, but a slow and continuous reduction in proximity that the brain is not naturally trained to interpret. As the spacecraft moves closer to the Sun, another important effect becomes visible, which is how radiation intensity increases with proximity. The Sun emits massive amounts of energy in all directions, but that energy spreads out over distance, which means the further you are, the more it is diluted. At Earth's distance, the energy is enough to warm the planet but not destroy it, while closer to the Sun, the same energy becomes increasingly dangerous. This relationship between distance and energy intensity is not intuitive because the brain does not naturally link empty space with energy dilution in a direct way. What makes this even more difficult to understand is that there is no visible gradient in space that shows this change. You do not see a clear boundary where the Sun becomes stronger or weaker. Instead, it is a smooth transition that only becomes clear when measured scientifically. The brain expects changes in environment to be visually obvious, but in space, many of the most important changes are invisible and only detectable through instruments. At this point, the Sun stops being just a bright object in the sky and becomes a reference point for understanding scale itself. It sits in a position where Earth-based intuition still tries to apply familiar logic, but the actual physics already operates on a completely different level of distance and energy. The brain continues to process the Sun using the same shortcuts it uses for nearby objects, but those shortcuts no longer match reality in a consistent way. The idea of distance also becomes tied more strongly to time at this scale. Since light takes 8 minutes and 20 seconds to reach Earth, any change on the Sun, such as a flare or surface activity, is not seen immediately. Instead, it is observed after a delay, meaning that even real-time solar activity is always slightly in the past from Earth's perspective. This creates a situation where the present state of the Sun is always hidden from direct human observation, and only its recent history is visible at any moment. This separation between actual state and observed state is small compared to deeper space distances, but it is the first clear example where time delay becomes part of normal observation. The brain does not naturally adjust for this delay when forming perception, so it continues to treat the sun as if it is being seen instantly, even though it is physically impossible for light to arrive without delay. As distance increases further into space, this delay will grow from seconds into minutes, then hours, then years, and eventually millions of years. But at the sun's distance, the 8-minute gap is the first clear signal that space is not just empty distance, but a structure where information itself takes time to travel. This realization is not immediate in perception, but it becomes unavoidable when the numbers are laid out clearly. In a solar system, everything is empty. The inner solar system looks simple when drawn on charts or seen in animations, with planets placed in neat rows and distances shown as clean gaps. But the real structure of this region is nothing like those simplified images, because the space between Mercury, Venus, Earth and Mars is not a set of small separations, but a vast stretch of mostly empty vacuum, where planets are extremely small compared to the distances that separate them. And this difference is the first point where the idea of space starts to break away from normal intuition in a very clear way. Mercury, the closest planet to the Sun, orbits at an average distance of about 57.9 million kilometers, and even this number is already difficult to connect to any Earth-based experience because there is no direct way to walk, drive, or fly across anything close to that scale in a continuous motion that the brain can track. Between Mercury and Venus, the distance changes constantly because both planets move in their own orbits, but the average gap still sits in tens of millions of kilometers, and this is already enough to make the region between them feel less like a shared space and more like isolated paths that rarely come close to each other in any stable way. Venus sits at about 108.2 million kilometers from the Sun, and when you compare this to Earth's orbit at about 149.6 million kilometers, the spacing between these inner planets begins to show something important that is not obvious at first glance, which is that the planets are not arranged like steps on a ladder, but more like separate moving paths that rarely align in simple ways. The brain tends to imagine planets as if they are placed at fixed distances, but in reality, they are constantly moving, and the gaps between them are always changing, which makes the idea of distance between planets far less stable than it appears in simplified models. Mars is at about 227.9 million kilometers from the Sun, and when you place Earth between Venus and Mars in your mind, the first thing that should stand out is not the planets themselves, but the space between them, because the distance from Earth to Mars can vary from about 54.6 million kilometers at its closest approach to over 400 million kilometers when they are on opposite sides of the Sun. This variation alone shows that planetary distance is not a fixed number, but a shifting range, and this shifting range removes any simple sense of proximity that the brain tries to assign when thinking about neighbouring planets. What becomes more important at this stage is not the planets themselves, but the emptiness between them, because if you take away the planets, what remains is not a structured environment, but a vast vacuum, where almost nothing exists at all in terms of matter. There is dust, scattered particles, and occasional small objects, but compared to the scale of space, these are almost negligible. The inner solar system is not filled with material waiting to be crossed. It is mostly empty space, with rare points of mass separated by enormous distances. This is where the first strong realization appears, which is that the solar system is not crowded in any meaningful sense, even though diagrams often make it look that way. If you were to scale down the planets to something you could hold in your hand and place them at correct relative distances, the nearest planets would still end up far apart in a way that removes any sense of visual grouping. Earth, Venus and Mars would not sit close together. They would be spread out across a space so large that most of it would be completely empty. And this emptiness is not a minor detail, but the main structure of the system. Mercury itself is not just close to the Sun. It is embedded in a region where solar radiation is intense, and space is still almost completely empty. The Sun dominates this region not because it fills space with matter, but because its gravity and light extend across distances that contain almost nothing else. Even in this inner region, where planets are relatively close compared to the rest of the solar system, the actual amount of matter compared to empty space is extremely small. Most of the volume between planetary orbits is vacuum, and this vacuum is not occasional or patchy. It is the default state of the region. When spacecraft move through this area, the emptiness becomes more than just a concept. It becomes a physical experience measured in time and distance. Missions traveling to Mars, for example, do not move through a dense field of objects. They travel through long stretches where nothing changes visually except the slow shrinking of Earth and the gradual appearance of Mars as a distant point. Even at high speeds, these journeys take months, and during that time, the spacecraft is not navigating obstacles but crossing continuous empty space that offers no landmarks or interruptions. Mars missions, including rovers and orbiters, highlight this scale in a practical way because they show how long it takes to move even within what is called the inner solar system. A journey to Mars is not a quick step outward. It is a long travel process where timing depends heavily on orbital alignment between Earth and Mars. Launch windows only open every 26 months or so because both planets must be in positions that reduce travel distance. Even then, the journey still takes around 6 to 9 months, depending on the mission design, which shows that even relatively nearby planetary travel requires extended time through empty space. The probes sent farther out, such as Voyager 1 and Voyager 2, make this emptiness even more obvious. These spacecraft have been travelling for decades and are still within or near the edge of the solar system. Despite continuous motion for over 40 years, their distance from Earth is still small compared to interstellar scales. This slow progress is not due to lack of speed alone, but due to the massive scale of space itself, where even fast-moving objects take extremely long periods to cross relatively small cosmic regions. As these probes travel outward, they pass through regions where particle density decreases further and solar influence weakens gradually. There is no sharp boundary where the solar system ends. Instead, there is a slow fading of solar effects across vast distances. This gradual transition makes it difficult for the brain to define a clear edge, because on Earth, boundaries are usually sharp and visible, while in space, boundaries are spread over enormous distances and are defined by changes in physical influence rather than visible lines. The spacing between Mercury, Venus, Earth and Mars also highlights another important distortion, which is the difference between planetary size and orbital distance. Planets are extremely small compared to the space they occupy. Earth, for example, has a diameter of about 12,742 kilometers, but the distance to its orbit around the Sun is 149.6 million kilometers. This means Earth itself is tiny compared to the path it travels, and even more tiny compared to the space around it. If you place Earth and Mars in correct scale, the distance between them is so large that both planets would appear as small isolated points with vast emptiness between them. The brain struggles with this because it tends to assume that objects in a system are related in size and spacing in a balanced way. On Earth, objects that are part of the same environment are usually close enough to interact. But in space, being part of the same system does not mean being close in any practical sense. Even light takes significant time to cross these distances. Communication between Earth and Mars can be delayed by several minutes, depending on their positions in orbit. This delay increases as distance grows, and it shows that even information transfer is affected by the emptiness of space. Signals do not move instantly. They travel across a vacuum where nothing speeds them up or slows them down except distance itself. The inner solar system also shows how motion does not reduce emptiness. Planets are constantly moving at high speeds around the Sun, but their motion does not fill space or reduce the gaps between them. Instead, it maintains the structure of separation, because each planet follows its own orbital path that never collapses into a shared cluster. This creates a system where movement is continuous, but proximity is always limited by scale. As you move from Mercury outward to Mars, the pattern remains consistent. There is no point where space becomes less empty. Instead, emptiness remains the dominant feature, and planets act as small, moving points within that emptiness. Even when multiple planets are within the same general region of the solar system, the distances between them remain so large that direct comparison to Earth-based spacing becomes meaningless. What makes this even harder to grasp is that human perception does not register emptiness as something meaningful. The brain focuses on objects, edges, and changes, not on absence. So when space is mostly empty, the brain effectively ignores the emptiness and only processes the planets as visible points. This creates a false impression that the system is more populated than it actually is, because the empty regions are not visually represented in perception. Outer solar system, the real shock. The outer solar system is where human intuition stops working in a clear and visible way, because everything that feels large or far in the inner system suddenly becomes tiny and compressed compared to the scale of space beyond Mars. And what looks like a structured set of planets in diagrams turns into something that is mostly empty distance, with a few massive objects floating far apart from each other, separated by gaps so large that no Earth-based experience can be used to understand them directly, without breaking the idea down into numbers that no longer feel connected to physical reality. Jupiter sits at about 778 million kilometers from the Sun, and even this distance already removes any remaining sense that the solar system is compact or tightly arranged, because Jupiter is not just farther out than Mars. It is placed in a region where the scale between objects starts to expand in a way that makes earlier distances look small in comparison, even though those earlier distances were already beyond human experience. Jupiter itself is massive, more than 11 times the diameter of Earth. But even with that size, it is still only a point when seen in the context of the solar system, because the space around it is so large that its physical size becomes insignificant compared to the orbit it occupies. Saturn comes even farther out at about 1.4 billion kilometers from the Sun, and this is where the first major shock in scale becomes clear in a practical sense, because the distance between Jupiter and Saturn is not a small step outward. It is another massive stretch of empty space, where nothing changes in a meaningful visual way during travel, except the slow shift of position over long periods of time. Saturn is famous for its rings, but even those rings are extremely thin compared to their width, and they exist within a region that is still dominated by emptiness. The rings do not fill space in a dense way. They are scattered particles spread across a wide orbital plane, which means even the most visually complex structure in the outer solar system is still mostly empty space. Uranus sits at about 2.9 billion kilometers from the Sun, and Neptune at about 4.5 billion kilometers. And by the time you reach these distances, the idea of outer planets stops, meaning a simple extension of the solar system, and starts meaning a completely different scale of separation, where each planet occupies its own isolated region of space, with enormous gaps between them. The distance from Saturn to Uranus alone is so large that if you tried to imagine it in Earth terms, it would erase any sense of continuity between them, because there is no gradual transition that feels natural to the brain at this scale. One of the most important ways to understand this region is through light travel time, because light is the fastest signal in the universe and still takes about 4 hours to travel from the Sun to Neptune. That means if the Sun suddenly changed in any way, Neptune would not know about it for 4 hours. This delay is not a small detail. It is a direct measurement of how large the solar system actually is, because even the fastest possible information transfer is slowed by the distance alone. At Earth, the delay is only about 8 minutes, but at Neptune it becomes hours, which shows how quickly scale expands as you move outward. This light delay also reveals something important about perception, because everything we see in the outer solar system is not current. It is always delayed information. When we observe Jupiter or Saturn through telescopes or spacecraft data, we are always seeing them as they were hours or even longer in the past, depending on their position. This means that even within our own solar system, real-time observation does not exist beyond a certain point, and what we call now is always slightly outdated when dealing with outer regions. The structure of space in this region also exposes one of the biggest illusions created by diagrams of the solar system. In most visual representations, planets are shown relatively close together, often with exaggerated sizes and reduced distances, so that everything fits on a page or screen. This creates a mental image where planets appear to form a compact system with clear spacing and recognizable order. But if you were to scale the solar system accurately, with correct planet sizes and real orbital distances, most of the structure would disappear visually, because the planets would become tiny points separated by vast empty regions that dominate the entire layout. In a correct scale model, Jupiter would be a small point far from the Sun, Saturn would be even farther and smaller in appearance, and Uranus and Neptune would be so distant that they would be almost impossible to include on the same visual frame, without shrinking everything to a level where planetary detail disappears completely. The brain struggles with this because it relies heavily on visual proportion, and when diagrams distort scale for clarity, they replace reality with something easier to understand but less accurate. Gas giants themselves are another source of misunderstanding in this region, because while they are physically enormous compared to Earth, they are still tiny compared to the space they occupy. Jupiter, the largest planet in the solar system, could fit more than 1,300 Earths inside its volume, yet it still occupies only a single point in its orbit around the Sun. Saturn, Uranus and Neptune follow the same pattern, where their massive size does not translate into any meaningful filling of space. Instead, they remain isolated bodies surrounded by almost complete emptiness. The distances between these planets are so large that even at high spacecraft speeds, travel takes years or decades. Missions to Jupiter can take several years depending on trajectory, and missions to Saturn take even longer. These journeys are not just long in time, they are long in a way that removes any sense of continuous movement through a filled environment. Spacecraft do not pass through dense fields of objects, they move through vacuum, where the only changes are the gradual shrinking of the Sun and the slow appearance of distant planets. Voyager 1 and Voyager 2 provide one of the clearest real examples of this scale. Launched in the 1970s, they passed Jupiter and Saturn decades ago and have continued moving outward ever since. Despite travelling for more than 40 years, they are still within the outer regions of the solar system, and their progress highlights how large these distances are in physical terms. Even at speeds of tens of thousands of kilometres per hour, the spacecraft still require decades to cross regions that, in diagrams, look relatively small and simple. Another important point in the outer solar system is how orbital paths stretch out in time. Planets like Neptune take about 165 Earth years to complete a single orbit around the Sun. This means that since its discovery, Neptune has not even completed a full orbit. This kind of timescale removes any human reference for motion, because no individual life experience can track a full planetary cycle. Motion in this region is not something that can be observed in real time from a human perspective. It is something that must be measured across generations. The emptiness between planets becomes even more dominant as you move outward. While the inner solar system is already mostly empty, the outer regions expand this emptiness to a much larger scale, where distances increase rapidly and objects become more isolated. There is no gradual filling of space, only increasing separation. This creates a structure where planets are more like isolated islands in a vast vacuum rather than members of a closely packed system. Even gravitational influence spreads across this emptiness without filling it. The Sun's gravity extends far beyond Neptune into regions like the Kuiper Belt and beyond. But this influence does not mean physical presence. It is an invisible force acting across space that contains almost no matter. This is another point where the brain struggles, because it tends to associate influence with proximity. But in space, forces can act across enormous distances without any visible connection. The outer solar system also shows how misleading scale comparisons can be when using Earth-based thinking. On Earth, large distances usually mean travel through environments filled with landmarks, terrain, and visible change. In space, large distances mean something completely different, which is travel through continuous vacuum with almost no change at all, except for position relative to distant objects. This lack of change removes the usual feedback system that the brain uses to measure progress. As you move from Jupiter to Neptune, the solar system does not become more complex in a visual sense, it becomes more empty in a spatial sense, with larger gaps between each major object and fewer secondary structures to break up that emptiness. The result is a system where most of the volume contains nothing that can be seen or touched, and where the few existing objects are separated by distances so large that their size becomes irrelevant compared to the space between them. The edge, Kuiper Belt, and Oort cloud. The outer edge of the solar system is not a clean boundary where space suddenly ends or changes. It is a slow-fading region where the influence of the Sun becomes weaker over extreme distances, while objects become fewer, smaller, and more spread out until the idea of a system itself starts to lose meaning. And this is where human intuition breaks again, because the brain expects edges to behave like walls or borders. But space does not work that way at all. Instead, it stretches outward in a gradual thinning that is difficult to notice unless you break it down carefully. Pluto is often the first name people associate with this region, but its real position in space is not a boundary marker. It is just one object among many that share a similar orbital zone far beyond Neptune. And even though it was once labelled as the 9th planet, that label does not match how the region actually works. Pluto orbits at an average distance of about 5.9 billion kilometres from the Sun, which already places it in a zone where sunlight is extremely weak compared to Earth, and where the Sun appears only as a very bright star rather than a large visible disk in the sky. From Pluto's surface, the Sun would look like a very intense point of light, but it would not provide the same warmth or presence that defines planets closer to it. The important part is not Pluto itself, but what surrounds it, because beyond Neptune's orbit lies the Kuiper Belt, a wide region filled with icy objects, small dwarf planets, and debris left over from the formation of the solar system. But even calling it a belt can be misleading, because it does not behave like a solid ring or a dense band of material. Instead, it is a very wide zone where objects are scattered across enormous distances, and most of the space between them is empty vacuum. The word belt suggests structure and density, but in reality, it is closer to a thin distribution of material stretched across billions of kilometres of space. The Kuiper Belt begins roughly at Neptune's orbit and extends outward to about 50 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun. That means this region stretches far beyond the outer planets and continues for billions of kilometres into space. But even across this wide region, the actual amount of matter present is extremely small compared to the volume it occupies. Most of the Kuiper Belt is empty space, with only occasional objects drifting within it, and even those objects are separated by distances so large that they rarely interact directly. Objects in the Kuiper Belt include bodies like Pluto, Eris, Haumea, and Makemake, but these names should not create the impression of a crowded region, because each of these objects is separated by millions or even billions of kilometres from others. If you were placed inside this region, you would not see a field of nearby objects. You would see almost nothing except distant points that barely change position over long periods of time. The brain tends to imagine clusters when it hears lists of objects, but in reality, those objects are spread so far apart that each one exists almost like a separate world, isolated in space. Travel through this region shows how scale changes perception in a direct way. Spacecraft that move into the Kuiper Belt do not pass through dense environments. They continue through long stretches of empty space with only occasional measurements of dust or particles. Even at high speeds, crossing this region takes many years, and the distance between objects means that there is almost no visual change for long periods of time. Voyager spacecraft have passed through parts of this outer region after decades of travel, and even after such long missions, they are still within the solar system's influence. Beyond the Kuiper Belt lies a region that is not directly observed, but is strongly supported by scientific models known as the Oort cloud. This is a theoretical structure that is believed to surround the solar system at extreme distances, possibly extending up to 100,000 astronomical units from the Sun, which is so far that the distance becomes difficult to express in familiar terms without losing meaning. The Oort cloud is thought to be a vast spherical shell of icy objects surrounding the solar system in all directions, not in a flat disk like the inner planets or Kuiper Belt, but as a huge cloud-like structure that defines the outermost gravitational influence of the Sun. Even though it is called a cloud, it is not a dense region. It is expected to contain small icy bodies separated by enormous distances, meaning that even within this outermost boundary, space is still mostly empty. The objects in this region are not tightly packed or visually connected. They are isolated bodies held loosely by the Sun's gravity at distances so large that the Sun itself would appear extremely small and faint from their position. What makes the Oort cloud especially difficult for human intuition is its scale compared to everything else in the solar system. If the inner solar system feels large and the outer planets feel even larger, then the Oort cloud stretches far beyond both in a way that removes any remaining sense of proportional comparison. It is not just farther away, it is so far that the distance between the Sun and the outer edge of the Oort cloud becomes a scale that cannot be easily compared to planetary distances without losing clarity. This is where time begins to distort perception even more strongly. Spacecraft that travel through the inner solar system take months or years to reach planets like Mars or Jupiter. But when you move outward to the Kuiper Belt and beyond, travel times expand into decades or even longer. Voyager 1, which launched in 1977, took decades just to reach the outer regions of the solar system. And even now, it continues to move outward, still not anywhere close to the hypothetical edge of the Oort cloud. At this scale, human lifetimes become too short to observe full transitions across regions of space, meaning that movement is measured in generations rather than years. The difference between decades and centuries becomes important when thinking about this outer region. Because while inner solar system travel might be measured in months or years, journeys to the far outer solar system would take timescales that exceed normal human planning. Even light, which is the fastest possible signal, would take years or even longer to cross parts of this region, and across the full span of the Oort cloud, the delay would stretch into timeframes that remove any sense of real-time connection. Pluto's role in this structure is not as a boundary, but as a reference point that sits inside a much larger field of similar objects. When Pluto was reclassified as a dwarf planet, it was not removed from the system. It was simply redefined as part of a broader population of objects that exist in the same region. This change reflects a shift in understanding, where instead of seeing the outer solar system as a structured set of planets ending at Pluto, it is now understood as a wide zone filled with many small icy bodies spread across vast distances. The Kuiper Belt itself is not uniform. It contains different types of objects with different orbits, some more stable than others, and some influenced more strongly by Neptune's gravity. This creates a loosely organized structure rather than a solid belt. But even this structure is so spread out that the term structure only applies in a very broad sense. The actual physical spacing between objects is so large that direct interaction between them is extremely rare on human timescales. When thinking about this region, the brain often tries to fill in the gaps by imagining it as more crowded than it actually is, because empty space is difficult to visualize. But in reality, if you removed all objects from the Kuiper belt, the change in visible space would be almost unnoticeable, because the majority of the region is already empty vacuum. This shows that what defines the region is not density, but gravitational influence and orbital paths rather than physical clustering. The Oort cloud extends this emptiness to an even greater level, where the distance between individual objects becomes so large that they are effectively disconnected from each other except through the Sun's weak gravitational influence. These objects are thought to be remnants from the early formation of the solar system, preserved in distant orbits that take extremely long times to complete, if they complete them at all within measurable time frames. The nearest star, Proxima Centauri. The moment you leave the solar system and try to measure distance to the nearest star, human intuition stops behaving like a reliable tool, because everything that still felt slightly understandable inside the solar system suddenly stretches into a scale where even the simplest comparisons stop working in any direct way. And Proxima Centauri becomes the first clear example of this shift, not because it is especially complex, but because it is the closest possible point outside our solar system and still sits at a distance that removes all Earth-based sense of proximity. Proxima Centauri is about 4.24 light-years away from the Sun, and this number alone already breaks normal perception, because a light-year is not a time measurement but a distance measurement based on how far light travels in 1 year, which means the distance is defined using the fastest known speed in the universe and still ends up producing a gap so large that it cannot be compared to anything inside human experience. Light travels about 300,000 kilometers every second, and even at that speed, it takes more than 4 years to cross the space between our Sun and this nearest star, which shows immediately that the gap is not small in any practical sense, even though it is called the nearest. To understand what this distance means in a more grounded way, imagine reducing the Sun to a simple object like a basketball, keeping its size fixed in that comparison, and then trying to place Proxima Centauri at the correct scale distance from it, because in that scale model, the nearest star would not be in the same room, or even in the same neighborhood. It would be far outside the city, placed at a distance that forces the brain to stretch beyond normal spatial thinking. This comparison is often used because it removes numbers and replaces them with physical separation that can be imagined in space. But even this version still fails to fully capture the emptiness between the 2 points. Because the distance is not just large, it is mostly empty vacuum, with almost no interaction or structure between the 2 ends. If you think about spacecraft instead of light, the scale becomes even more extreme. Voyager 1, one of the farthest human-made objects, is travelling at a speed that seems fast in human terms. But even at that speed, it would take more than 40,000 years to reach Proxima Centauri. This number does not just represent a long journey, it represents a timescale that goes beyond recorded human history by a massive margin, meaning that even if the spacecraft had been launched when early civilizations were forming, it would still not have reached its destination by now, and would still be travelling through empty space without any meaningful change in environment for thousands of years. This comparison between spacecraft speed and interstellar distance highlights a key failure in human perception, because on Earth, speed and distance are usually linked in ways that allow planning and expectation. You can estimate how long a trip will take based on how fast you move and how far you travel, and that system works well within Earth distances. But once you scale that system up to interstellar space, the same logic stops producing meaningful results because the distances are so large that even the fastest possible motion becomes almost irrelevant when measured against them. The space between the Sun and Proxima Centauri is not a continuous environment in any familiar sense. It is not filled with objects or structures that can be used as reference points during travel. Instead, it is almost completely empty vacuum, with only rare particles scattered across enormous distances. This emptiness is not something that can be seen directly because there is nothing there to reflect or emit light in a way that forms visible structure. As a result, the brain cannot build a visual map of the journey. It can only imagine a blank stretch with a point of origin and a point of destination, with no meaningful detail in between. When you look at Proxima Centauri from Earth, what you are seeing is not its current state, but its state from about 4.24 years in the past, because that is how long its light takes to reach us. This means that every observation of that star is delayed information, not real-time data. If something changed on Proxima Centauri today, we would not know about it until more than 4 years later. This delay is small compared to deeper space distances, but it is the first clear example of how even the nearest star is already separated from us by both space and time in a measurable way. This light delay creates a situation where the concept of now stops being universal across space. On Earth, now is shared across all observations because light travel time is effectively instantaneous at human scale. But once you reach interstellar distances, now becomes local rather than global, meaning that each point in space has its own version of what is currently happening, and these versions are separated by years of delay depending on distance. The brain does not naturally account for this when forming perception, so it continues to treat distant stars as if they exist in the same present moment, even though physically they are always being seen in the past. Proxima Centauri is part of a triple star system known as Alpha Centauri, but even within this system, distances remain large compared to solar system scales. The stars are gravitationally linked, but still separated by distances that would take thousands of years for spacecraft to cross. This shows that even systems containing multiple stars are not tightly packed structures, but loosely connected groups where each star still occupies its own large region of space. If you expand this idea further, it becomes clear that the concept of nearest star itself is misleading to human intuition. The word nearest suggests closeness in a way that implies accessibility or familiarity. But in reality, Proxima Centauri is still so far away that it cannot be reached within any normal human time frame using current technology or even foreseeable improvements. The label nearest only makes sense when compared to the even larger distances to other stars. But within absolute terms, it is still an extreme separation. The brain struggles most at this stage because it tries to scale distance using internal reference points built from Earth experience. On Earth, distances are measured in meters, kilometers, and travel times that fit within hours or days. Even the Moon, which already stretches this system, can still be conceptualized as a reachable object with current technology. But Proxima Centauri removes that possibility entirely, because no direct physical experience exists that can bridge the gap in a meaningful way. The distance is too large for travel, too empty for visual reference, and too delayed for real-time understanding. Another important aspect is how motion becomes meaningless at this scale. On Earth, movement is something you can observe directly, whether it is a car, a plane, or even a spacecraft launching into orbit. But between stars, motion happens in a way that is almost invisible over short timescales. A spacecraft moving toward Proxima Centauri would appear completely still for most of human observation, because the change in position is so small compared to the total distance involved. Even after decades, the shift would still be difficult to notice without precise measurement tools. This creates a disconnect between what motion actually is and how it is perceived. The brain expects movement to produce visible change over short periods, but in interstellar space, movement only becomes meaningful when measured over extremely long periods of time. This forces all understanding of motion to shift from direct observation to abstract calculation, which removes it from normal perception entirely. Even the idea of separation becomes difficult to define clearly at this scale. On Earth, separation means something you can cross or reduce with effort. But between stars, separation becomes a fixed structure that does not change meaningfully over human timescales. Proxima Centauri is not just far away, it is locked into a position of extreme distance that remains constant from a human perspective, even though both stars are moving through the galaxy at high speeds. The galaxy itself is in motion, and Proxima Centauri is moving within it. But these movements do not reduce the distance in a way that the brain can perceive. Instead, everything moves together on scales that are too large and too slow to register as change. This creates a situation where distance is not just large, but stable in appearance, even though it is constantly shifting in reality. At this point, the nearest star stops being just a reference point and becomes a clear example of how space removes familiar structure from perception. It is close only in comparison to other stars, but in absolute terms, it is already so far that no direct human experience can match it. The brain continues to treat it as a point of light in the sky, but behind that simple appearance is a separation so large that it defines the first real step outside the solar system into true interstellar space. The Milky Way problem. The moment you step beyond the nearest stars and try to understand the Milky Way as a whole structure, human perception reaches a limit that is even harder to deal with than interstellar distance, because now the problem is not just how far one object is from another, but how to understand a system that contains hundreds of billions of stars spread across a structure so large that no direct visual model can hold it in the mind at once. And this is where scale stops being something you can reduce into everyday experience and becomes something the brain can only process in fragments. The Milky Way is about 100,000 to 200,000 light-years wide, and this range already shows one of the first issues in understanding it, because even the size is not a single fixed number, but a range depending on how the galaxy is measured, which means the boundary itself is not sharp or clearly defined, but gradually fades into regions where stars become more spread out and less dense until they eventually blend into intergalactic space. This alone removes the idea of a clear edge, because there is no wall or boundary where the galaxy simply stops. Instead, there is a slow reduction in star density that makes the outer regions less defined. Inside this structure are roughly 100 to 400 billion stars, and that number is so large that it stops functioning as a countable quantity in any meaningful way for human perception. On Earth, large numbers are still connected to physical groups, like crowds, cities, or populations, but at this scale, individual stars cannot be mentally tracked as separate objects. The brain cannot hold 100 billion individual points in any direct way, so it compresses them into categories like many stars or a dense field of light, even though the actual distribution is highly varied and structured. The Sun is located in a region called the Orion Arm, which is not a central position in the galaxy, but a smaller spiral arm located between larger structures. This means our solar system is not at the center of the Milky Way, nor at its edge, but somewhere in between, embedded in a curved arm of stars, gas, and dust. The Orion Arm itself is not a compact region. It is a stretched structure thousands of light-years wide, containing many star systems separated by large distances. And even within this arm, the spacing between stars remains so large that direct interaction between them is extremely rare. When you try to place the solar system inside a mental model of the Milky Way, the first major issue is scale placement. The Sun is just one star among hundreds of billions, and its position within the Orion Arm is not marked by any visible landmarks that would make it easy to locate without scientific mapping. There is no visual reference from Earth that can show the structure of the galaxy in real time, because we are inside it, not outside it, which means we cannot step back and view it as a complete object. This creates a major visualization problem, because most images of the Milky Way are either artistic interpretations or composites based on data, not direct photographs of the galaxy from outside. There is no way to capture the entire structure of the Milky Way in a single image from our position inside it, which forces all representations to rely on reconstruction rather than direct observation. The brain tends to treat these images as if they are simple pictures of a real object, but in reality, they are assembled views built from partial data. The structure of the Milky Way is a rotating spiral galaxy, meaning that all stars within it orbit around a central region over extremely long timescales. The Sun itself is moving through this galaxy at a speed of about 828,000 kilometers per hour. But even at that speed, it takes roughly 225 to 250 million years to complete a single orbit around the galactic center. This means that since the time of the dinosaurs on Earth, the Sun has not even completed a quarter of its galactic orbit, which shows how slow motion becomes when scaled to galactic distances. This galactic rotation is not something that can be observed in real time by humans because the timescale is too large. On Earth, motion is something that can be tracked continuously, but in the Milky Way, motion is measured in millions of years, which removes it from direct perception entirely. The stars do move, but the movement is so slow relative to human lifespans that it appears almost static when viewed from our perspective. The Milky Way also contains different regions with different densities of stars, gas and dust. But even the densest regions are still mostly empty space when compared to Earth-based environments. Stars are not packed closely together like objects in a crowd. They are separated by distances measured in light years. Even in regions that appear bright and dense in images, the actual spacing between individual stars remains extremely large compared to their size. If you place stars at correct scale, most of the galaxy would be empty space. The visible brightness in the night sky comes from many distant stars combined along lines of sight, not from tight clustering in physical space. This is another key point where perception fails, because the brain interprets brightness as density. But in reality, brightness in the galaxy often comes from distance, layering, rather than actual proximity. From Earth, we see the Milky Way as a faint band of light stretching across the sky. But this appearance is not a direct view of the galaxy's structure. It is the result of looking through a flat plane of stars from inside the disk. The brightness is caused by looking along dense regions of the galactic plane, where many stars overlap in our line of sight. If you were outside the galaxy, the Milky Way would appear as a spiral structure, but from inside, it appears as a band because we are embedded within its disk. This internal position creates a major limitation in understanding the full shape of the galaxy, because we cannot step outside it to compare its structure visually. All measurements of shape, size and structure must be done through indirect observation and mapping, using star positions, distances and motion data collected over time. This means our understanding of the Milky Way is built from reconstruction rather than direct observation. Another important factor is the spacing between stars within the galaxy. Even though the Milky Way contains hundreds of billions of stars, the average distance between them is still extremely large. The Sun's nearest stellar neighbour, Proxima Centauri, is already more than 4 light-years away, and this is within a relatively local region of the galaxy. In other parts of the Milky Way, distances can be even larger, especially in outer regions where star density decreases. This shows that even inside a galaxy filled with hundreds of billions of stars, space is still mostly empty. The galaxy is not a dense cluster. It is a wide structure with isolated points of matter separated by enormous gaps. The brain struggles with this because it assumes that large numbers automatically mean closeness or density. But in galactic terms, large numbers are spread across such a vast volume that emptiness remains the dominant feature. As you move away from the Sun's position in the Orion Arm toward other parts of the galaxy, the scale does not become easier to understand. It becomes more difficult because there are fewer familiar reference points. The center of the galaxy contains a dense region around a supermassive black hole, but even this region is not a solid object. It is a gravitational center surrounded by stars moving in complex orbits. The outer regions of the galaxy extend far beyond this, gradually thinning out until they transition into intergalactic space. The idea of an edge of the Milky Way does not exist in a strict sense. There is no defined boundary where the galaxy ends. Instead, there is a gradual decrease in star density that becomes less and less noticeable as you move outward. This lack of a clear boundary makes it difficult for the brain to define where the galaxy stops, because human perception relies heavily on edges and limits to define objects. Even the motion of stars within the galaxy does not create visible structure over short timescales. Stars orbit the galactic center, but their movement is so slow relative to human observation that the overall structure appears stable. This stability is misleading because the galaxy is in constant motion, but that motion operates on timescales that are far beyond direct perception. At this stage, the Milky Way becomes a structure that cannot be fully visualized as a single object. It is too large, too spread out, and too dynamic over long timescales for the brain to build a complete mental image. Instead, it exists as a set of partial understandings, where individual regions like the Orion Arm, galactic center, and outer disk are understood separately but never fully combined into a single clear picture that matches reality in full scale. Star density illusion plus the invisible motion problem. The way galaxies look in most images creates one of the strongest false impressions in astronomy, because when people see bright clusters of stars packed together in glowing shapes, the mind automatically assumes that space is crowded, active, and filled with objects close to each other. But the real structure of galaxies is almost the opposite, since even inside regions that look dense and bright, most of the volume is still empty vacuum, and the stars themselves are separated by distances so large that direct proximity between them is extremely rare on any human timescale. A galaxy like the Milky Way contains hundreds of billions of stars. Yet those stars are not packed tightly together like objects in a group. Instead, they are spread across distances measured in light years, which already removes any Earth-based idea of closeness, because on Earth even large cities still feel continuous, but in space, even a region filled with stars is mostly empty when compared to the size of the space it occupies. The average distance between stars is so large that if you place the Sun and its nearest neighbour, Proxima Centauri, at correct scale, you would find that most of the space between them contains nothing that can be seen or touched, only vacuum stretching across vast gaps. This is where the first major illusion begins, because images of galaxies are usually captured using long exposure techniques or combined data that collect light from many sources over time. And when all that light is compressed into a single image, it creates the appearance of a dense field of stars, even though, in reality, those stars are separated by enormous distances along different depths in space. What looks like a crowded cluster in a picture is often a layering effect, where distant stars overlap visually from a single viewpoint, but are not actually close to each other in physical space. The brain struggles with this difference because it relies heavily on visual density as a signal for closeness. So when it sees many bright points in a small area of the sky, it assumes those points are near each other, even though in galactic terms they can be separated by hundreds or thousands of light years. This creates a strong mismatch between appearance and structure, because brightness does not equal proximity, and density in an image does not represent physical clustering in space. Distance between stars is not measured in kilometers in any meaningful way because the numbers become too large to handle easily. So astronomers use light years, which already shifts the scale into a different system of thinking. 1 light year is about 9.46 trillion kilometers, and even within a galaxy filled with stars, most separations are measured in multiple light years. This means that even light, the fastest known thing in the universe, takes years to cross the distance between neighbouring stars, which already shows how empty space is even inside dense regions. If you imagine trying to travel between stars using any form of spacecraft, the scale becomes even more extreme, because even at speeds far beyond anything currently achievable for humans, the travel time still stretches into thousands or tens of thousands of years. This removes the idea that galaxies are environments that can be crossed or explored in a direct sense, because even moving from one star system to another is a process that exceeds normal human timescales by a massive margin. Despite the large number of stars, the probability of stars colliding with each other is extremely low. This is because space is so large compared to the size of stars that even in regions where stars are relatively dense, the distance between them is still enormous. Stars are not packed tightly enough for frequent collisions, and most of the time they pass through their orbits without ever coming close to another star. This makes galaxies stable structures over long periods of time, not because they are rigid, but because the emptiness between stars prevents constant interaction. The reason galaxies often appear crowded in images is partly due to how light is captured and partly due to how human vision processes information. Cameras collect light over long exposures, allowing faint stars that are too dim for the human eye to see individually to become visible in the final image. When these faint points are added together, they create the impression of a dense star field, but this density is visual rather than physical. It comes from accumulation of light over time, not from actual closeness between objects. Another reason for this illusion is perspective compression. When looking at a galaxy from inside or viewing distant parts of it, many stars align along the same line of sight. This alignment causes their light to overlap in the final image, making them appear closer together than they actually are. In reality, one star might be hundreds of light years behind another, but from a single viewing angle, they appear to sit in the same region of space. As a result, galaxies that look like tightly packed spirals or glowing clouds are actually systems where most of the volume is empty space, and the visible structure is created by the distribution of stars along large-scale patterns rather than physical clustering. Spiral arms, for example, are not solid arms filled with stars. They are regions of slightly higher star density where stars pass through over time, creating a pattern that looks continuous from a distance but is actually made of separated points. This leads directly into the problem of invisible motion, because while stars appear fixed in place in short-term observation, they are actually moving constantly through space at high speeds. Each star in a galaxy orbits the galactic center, and these orbits are not short or quick. They take hundreds of millions of years to complete, which means that any motion happening on smaller timescales is almost impossible to detect directly. The Sun, for example, moves through the Milky Way at about 828,000 kilometers per hour, which sounds extremely fast in Earth terms. But when placed against the scale of the galaxy, this speed becomes almost negligible. Even at this speed, it takes around 225 million years for the Sun to complete one full orbit around the galactic center, which means that during the entire history of complex life on Earth, the Sun has only completed a small portion of its galactic journey. Because of these timescales, motion in galaxies is not something that can be observed in real time by humans. Stars do not appear to move across the sky in any noticeable way during a human lifetime, so the galaxy looks static even though it is constantly changing shape over millions of years. This creates the invisible motion problem, where movement exists but cannot be directly seen because it happens too slowly compared to human perception. The same issue applies to galaxies themselves moving through space. Galaxies are not fixed in place. They move within clusters and interact with each other over long periods of time. The Milky Way is moving toward the Andromeda galaxy, and this motion is real and measurable, but it will take billions of years for any significant interaction to occur. From a human point of view, this motion is effectively invisible because no change can be observed within a meaningful time frame. Cosmic timescales erase normal reference frames because everything that moves does so on a scale that is too large to track directly. On Earth, motion is defined by visible change over seconds, minutes, or hours. But in galaxies, motion requires millions or billions of years to produce visible differences. This means that the brain cannot use its normal system of tracking change to understand galactic motion, because the changes happen far too slowly to register. Even when motion is measured scientifically, it does not translate into perception. We know that stars orbit, galaxies rotate, and clusters shift. But none of these processes can be seen happening directly. Instead, they are reconstructed through data collected over long periods of observation, where small changes in position are recorded and then used to calculate motion over time. This turns motion into something abstract rather than something visible. The edge of visibility, the edge of what we can see in the universe, is not a physical boundary where space ends or where matter stops existing. It is only the limit of how far light has had enough time to reach us since the beginning of the universe. And this creates a situation where visibility is not based on distance alone, but on time, because everything we observe is tied to how long light has been travelling through space before reaching Earth. And this is where the idea of edge becomes misleading in a very important way. The observable universe is about 93 billion light-years wide, and this number already creates a major shift in understanding, because it is not just a large distance, it is a limit defined by time and expansion combined, meaning we can only see objects whose light has had enough time to reach us since the universe began about 13.8 billion years ago. This creates a situation where we are not seeing the universe as it is now, but as it was at different points in its history, depending on how far the light has travelled. The age of the universe, about 13.8 billion years, might seem like it should set a clear limit on how far we can see. But expansion changes this completely. Space itself has been expanding while light travels through it, which means that objects we see from very early times are now much farther away than they were when the light left them. This creates a mismatch between light travel time and current distance, where an object might have emitted light billions of years ago, but is now far beyond that original position due to the stretching of space itself. This is where the expansion paradox becomes important, because it shows that there are objects in the universe whose light we can see, even though they are now far beyond the distance that light could travel in the age of the universe. This happens because space is not fixed. It expands over time, carrying galaxies farther apart as the universe evolves. As a result, some regions that we observe are effectively unreachable, not because light cannot travel, but because the space between us and those regions is expanding faster than light can close the gap. The idea of a cosmic horizon comes from this limit, and it represents the boundary of what we can ever observe, not because there is nothing beyond it, but because light from beyond that boundary has not had enough time or is prevented by expansion from ever reaching us. This horizon is not a physical wall, it is a limit of information, meaning that anything beyond it is permanently hidden from observation, not because it does not exist, but because its light can never reach us under current cosmic conditions. When we look at deep space images like the Hubble Deep Field or the James Webb Space Telescope Deep Field, what we are seeing is not just distant objects, but different layers of time compressed into a single image. Each small point of light in these images is often an entire galaxy, and each galaxy is seen at a different stage of its past depending on how long its light has been travelling. Some of these galaxies are seen as they were billions of years ago, close to the early formation of the universe, which means these images are not snapshots of space as it exists today, but layered records of time spread across vast distances. Each pixel in these deep field images can represent an entire galaxy, which means that what appears as a simple speck of light actually contains hundreds of billions of stars, planets, and systems, all compressed into a single point of observation due to distance and resolution limits. The brain tends to interpret images as direct representations of objects, but in this case, the image is not showing structure in a simple way. It is showing layers of distance, brightness, and time all combined into one view. When we look deeper into space, we are also looking further back in time. The concept of look-back time becomes essential here, because every object we see in the universe is being observed as it was when the light left it. A galaxy that is 10 billion light-years away is being seen as it was 10 billion years ago, which means we are not observing its current state, but a version of it from a time when the universe itself was much younger and structured differently. This creates a situation where deep space observation is not just spatial mapping, but time mapping as well, because distance and time are directly connected through the speed of light. The farther we look, the further back in time we see, and this turns the universe into a layered structure where different regions represent different ages of cosmic history, all visible at once from a single point of observation. Galaxy clusters add another level to this structure, because galaxies are not evenly spread out in space. They are grouped into clusters and superclusters connected by long filaments of matter. These filaments are part of what is known as the cosmic web, a large-scale structure where galaxies are arranged along threads of dark matter and gas, forming patterns that stretch across hundreds of millions of light-years. Between these filaments are vast voids, regions of space that contain very few galaxies and very little matter, and these voids can be larger than entire galaxy clusters. This creates a foam-like structure in the universe, where matter is concentrated along thin strands and sheets, while most of the volume is empty space. The brain struggles to understand this, because it expects structures to be filled or solid. But in cosmic scale, structure is defined by distribution, not density. Superclusters, such as the Laniakea supercluster, show how galaxies can be grouped into even larger structures that span hundreds of millions of light-years. These superclusters are not bound in a rigid way. They are defined by gravitational flow, where galaxies move toward common regions of mass over long timescales. Even these massive structures are not stable in a fixed sense. They are part of a dynamic system, where gravity slowly shapes movement over billions of years. The cosmic web itself is not something that can be seen directly in normal observation. It is reconstructed from galaxy surveys and simulations based on large datasets. What appears in visualizations as a web-like pattern is a map of where matter is concentrated, not a direct image of a physical object. This again creates a mismatch between perception and reality, because the brain tends to interpret visual patterns as direct shapes. But in this case, the pattern is a statistical structure built from distribution of matter across extreme distances. At this scale, the universe begins to look less like a collection of objects and more like a large structure defined by empty space and thin connections of matter. Most of the volume is void, and galaxies occupy only small regions along filaments. This means that even though the universe contains enormous amounts of matter, it is still dominated by emptiness when measured by volume. The ultimate distance problem appears when considering how light travel and expansion interact over time. Light can only travel at a fixed speed, but space itself is expanding, which means that some regions of the universe are moving away from us faster than light can travel toward them. This creates a limit where certain galaxies will never be reachable or observable beyond a certain point, even in principle, because the space between us and them expands faster than information can cross it. Cosmic inflation, which is a rapid expansion phase that occurred in the very early universe, helps explain why the universe is so large and uniform at large scales, but it also contributes to the idea that distance is not fixed. Inflation stretched space extremely quickly in a very short time, setting the stage for the large-scale structure we see today. While inflation itself is not happening at the same rate now, the expansion of the universe continues, and this ongoing expansion changes how distances behave over time. Because of expansion, distance in the universe is not a stable measurement. Two galaxies that are currently far apart may become even farther apart over time, and in some cases, the space between them expands so much that light emitted now will never reach certain regions. This B7 reeks the normal idea that distance is something that can always be crossed given enough time, because in an expanding universe, time alone is not enough to guarantee connection between 2 points. At this level, distance stops behaving like a simple measurement and becomes something tied to the structure and evolution of space itself. The observable universe is not a fixed sphere of matter, but a dynamic region defined by how far light has travelled since the beginning of time, and how space has expanded during that journey. Everything inside it is part of a layered system of time, distance, and expansion that cannot be reduced to simple numbers without losing the structure that gives those numbers meaning. Why the brain fails. At this point in the journey, after moving from Earth to the Moon, from the Moon to the Sun, from the planets to the edge of the solar system, from nearby stars to the Milky Way, and from the Milky Way to the observable universe, a strange question begins to appear. The question is not about astronomy anymore. It is about us. Why does every step outward feel harder to understand than the one before it? Why do the numbers become less meaningful the larger they get? Why can we learn the facts, repeat the measurements, and even understand the science, yet still feel completely disconnected from the actual scale of what we are talking about? The answer is surprisingly simple. The human brain was never built to understand the universe. It was built to survive on Earth. That sounds obvious at first, but the consequences of that fact are much bigger than most people realize. Every part of your perception, every instinct about distance, size, motion, and space was shaped by a world that exists within a very narrow range of scales. For almost all of human history, the distances that mattered were the distances a person could walk, run, throw, climb, or see with their own eyes. The difference between 10 meters and 100 meters mattered. The difference between 1 kilometer and 10 kilometers mattered. Understanding where food was, where danger was, and where shelter was could determine whether you survived another day. Nothing in that environment prepared the human brain for a galaxy 100,000 light years across. Nothing in that environment prepared the human brain for a universe 93 billion light years wide. Nothing in that environment prepared the human brain for objects so distant that their light began travelling toward Earth before human beings even existed. The result is that our brains are incredibly powerful in some situations and surprisingly limited in others. We are excellent at understanding scales that fit inside everyday experience. We are terrible at understanding scales that exist far beyond it. That is not because we lack intelligence, it is because the systems inside the brain were optimized for survival, not for cosmic understanding. Think about how your brain normally understands distance. If someone tells you that a tree is 20 meters away, you immediately form a mental picture. You know roughly how far that is because your brain has spent a lifetime collecting experiences involving similar distances. If someone says a building is 500 meters away, you can still picture it. If someone says a city is 100 kilometers away, the image becomes less detailed, but it still exists. Then something strange happens. As the numbers continue growing, the pictures begin disappearing. 1 million kilometers, 100 million kilometers, 1 billion kilometers, 1 trillion kilometers. The numbers continue increasing, but the mental image stops growing with them. Eventually, the brain gives up. It stops trying to visualize the distance and replaces it with a simple label: far away. That is all that remains. This is one of the biggest limitations in human cognition. The brain does not truly understand large numbers. It compresses them, it simplifies them, it reduces them into categories that are easier to manage. Once a quantity becomes too large, the difference between one enormous number and another enormous number starts fading away. Mathematically, the difference between 1 billion and 1 trillion is enormous. 1 trillion is 1,000 times larger. Yet for many people, both numbers create almost the same feeling. Both simply mean very large. The same thing happens with distance. The distance to the moon feels far. The distance to the sun feels extremely far. The distance to the nearest star feels impossibly far. But once distances start being measured in light years, thousands of light years, millions of light years, and billions of light years, the differences between them begin collapsing inside the mind. The numbers continue growing, but our intuition stops growing with them. This happens because the brain struggles with exponential scales. Human perception works best when changes happen gradually. If a road becomes twice as long, we can understand that. If a building becomes twice as tall, we can understand that. If a trip takes twice as much time, we can understand that. But the universe does not grow in neat, comfortable steps. The jump from Earth to the moon is huge. The jump from the moon to the sun is vastly larger. The jump from the sun to the nearest star is even more extreme. The jump from one star to an entire galaxy is beyond that. Then galaxies themselves become tiny pieces inside structures that stretch across billions of light years. Each step multiplies the previous scale so dramatically that the brain loses its ability to build meaningful comparisons. This creates what could be called a neural scaling limit. The human mind can process addition reasonably well. It can process multiplication with effort. But once scales become overwhelmingly exponential, perception breaks down. The numbers no longer connect to experience, and without experience the brain struggles to attach meaning to what it is hearing. That is why astronomy often feels strange compared to other sciences. When you hear that a whale weighs many tons, your brain can roughly imagine a large animal. When you hear that Mount Everest is nearly 9 kilometers high, your brain can roughly imagine a very tall mountain. When you hear that the observable universe is 93 billion light-years wide, there is nothing to connect that statement to. No experience exists that can serve as a bridge between the number and genuine understanding. The brain therefore uses a shortcut. It turns reality into symbols. Instead of understanding the actual distance, it stores a simplified concept. Instead of building a detailed model, it stores a label. Instead of visualizing the true scale, it replaces it with an abstract idea. This is why people can spend years reading about astronomy while still feeling shocked when they encounter a new comparison that suddenly makes a distance seem real. The facts were always there. The understanding was not. To cope with this problem, human beings develop tools that allow us to shrink reality into forms the brain can handle. Every scientific image, every scale model, every diagram, every analogy, and every animation is part of that effort. In a sense, scientific visualization is a necessary lie. Not a lie in the sense that it is false, but a lie in the sense that it deliberately distorts reality so the brain can understand it. Think about every picture of the solar system you have ever seen. The planets are usually shown close together. Their sizes are often enlarged. Their distances are compressed. Their orbital paths fit neatly inside a frame. None of that is what the solar system actually looks like. If the planets were shown at correct scale and correct distance, most images would appear almost empty. The planets would be tiny points separated by enormous stretches of blank space. The image would become accurate, but it would stop being useful. So the distances are compressed. The sizes are adjusted. Reality is reshaped into something the brain can work with. The same thing happens with maps. A map is not reality. A map is a simplified representation of reality. The roads on a map are not the actual roads. The rivers are not the actual rivers. The cities are not the actual cities. The map leaves out almost everything that exists and keeps only the information needed for a specific purpose. Without that simplification, the map would become useless. The universe presents the same challenge. Reality is too large to fit inside the mind directly, so we create cognitive maps. We build models, we create diagrams, we invent comparisons, we shrink impossible scales into understandable forms. When someone says that if the sun were the size of a basketball, the nearest star would be another city away, that comparison is not reality. It is a cognitive shortcut designed to help the brain approach reality. When someone says every point in a deep field image is an entire galaxy, that statement acts as a bridge between what the eye sees and what actually exists. When someone says the Milky Way contains hundreds of billions of stars, they are using language to compress something that cannot be directly visualized. These shortcuts are necessary because the brain cannot store the universe in its raw form. It must reduce it. It must simplify it. It must transform it into something manageable. That process of compression is happening constantly, even when we do not notice it. The word galaxy itself is a compression. The word universe is a compression. The phrase observable universe is a compression. Behind each term sits an amount of information so vast that no human mind could ever hold all of it at once. The brain survives by replacing overwhelming complexity with manageable concepts. That strategy works remarkably well for everyday life, but it creates problems when trying to understand reality at its largest scales. Because eventually the simplification becomes so effective that we forget how much has been removed. We hear the word galaxy and imagine a shape. We hear the word universe and imagine a structure. We hear the word distance and imagine a measurement. What we often fail to realize is that these words are standing in place of realities far larger than the images they create. And this leads to the final scale reset. Forget the numbers for a moment. Forget the diagrams. Forget the labels. Start with Earth, the place where every human story has happened. A world that feels enormous when standing on its surface, where crossing oceans requires vast effort, and where entire civilizations can exist without seeing one another. Then pull outward and place Earth inside the solar system, where our planet immediately shrinks into a tiny object orbiting a star among immense stretches of mostly empty space. Pull farther outward and focus on the Sun itself, the object that dominates our solar system so completely that it contains almost all of its mass, yet becomes only one ordinary star among countless others. Keep moving outward until that single star disappears into the Milky Way, a galaxy containing hundreds of billions of stars spread across distances so large that light itself requires 100,000 years to travel from one side to the other. Keep moving outward again until the Milky Way becomes only one galaxy among many, part of a larger cosmic structure stretching beyond anything human beings evolved to imagine. Then continue farther still until galaxies themselves begin shrinking into points scattered across the observable universe, connected by immense structures, separated by vast regions of emptiness. At that scale, Earth is gone, the solar system is gone, the Sun is gone, the Milky Way is gone. The familiar reference points that shaped human perception disappear completely, leaving only the reality that has been there all along, operating according to physical laws, whether human beings can intuitively understand it or not. This is not the edge of imagination. This is measured physics.